Hi and Assalamualaikum everyone. Today we are going to present about the volumetric analysis of determination vitamin C concentration in food industry. Now I will begin with the introduction of volumetric analysis. Volumetric analysis is also known as titration, and it is a quantitative chemical analysis method that used to determine the concentration of a substance by measuring the volume of a solution of known concentration that need to react completely with solution of unknown concentration, which are the analyte. In this experiment, volumetric analysis used to determine the vitamin C concentration in a sample by redox titration with iodine solution. For your information, vitamin C is an essential antioxidant needed by the human body. During the titration, iodine oxidized ascorbic acid to dihydroascorbic acid while being reduced to iodide, just like the chemical equation below. The endpoint is detected when excess iodine reacts with starch indicator to produce blue black color. So, this method is effective from testing vitamin C contained in tablets, juices, and fruit or vegetable samples. Alright, now I will explain about the definition of titration in food industry. So, the titration use analytical technique in the food industry to determine the concentration of various substances in food. In food industry, titration is essential for guaranteeing the product quality, safety, and compliance with regulatory standards. By measuring specific chemical components such as acidity, salt, sugar, and preservative levels, food manufacturers can maintain the consistency in taste, shelf life, and nutritional value. Next, what is the type of the titration that used to determine the vitamin C? So, the titration used is redox titration. Basically, this titration works by the ascorbic acid that acts as a reducing agent, and it reduces iodine to iodide. At the same time, ascorbic acid oxidizes to dihydroascorbic acid. There is two types of redox titration used, which is direct titration. Direct titration is use a prepared iodine solution, and the iodine is added directly to the solution containing vitamin C. The other one is indirect iodometric titration, where they use potassium iodate to generate the iodine during the titration, and the analyte in this experiment is vitamin C, which is the ascorbic acid. The titrant is iodine solution, or the iodine that generated from the potassium iodate, and the indicator is the starch that will turns blue-black when iodine is present.
Okay, let's explore the science behind this titration process together. First, we begin the redox reaction theory. Ascorbic acid, or known as vitamin C, will act as the reducing agent where it will lose electrons. In the titration process, it reacts with a titrant, which is iodine, that is an oxidizing agent. During the reaction, vitamin C is oxidized while the titrant is reduced. The transfer of electrons is what we call a redox reaction. The chemical equation shown proves that the ascorbic acid oxidized to become dihydroascorbic acid, while iodine is reduced to become iodide. Next, we apply the concept of volumetric analysis. Just like Izlin has introduced before in the introduction part, in this case, the volume of iodine used can help us to calculate the vitamin C concentration in a food sample. Then comes the rule of stoichiometry. This involves using mole ratios from a balanced chemical equation to relate the amount of titrant used to the amount of vitamin C in the sample. Since the ratio between ascorbic acid or vitamin C and iodine is 1:1, the number of moles of iodine used directly tells us the number of moles of ascorbic acid present. And lastly, we use indicators to visualize the reaction. With the iodine method, the indicator used is starch solution. The yellow color of iodine will turn into dark blue with the presence of starch. The blue color appears once all the vitamin C has reached, which is our endpoint in this redox titration. These four theories work together to make redox reaction a precise and practical tool for measuring the vitamin C, helping the food industry to maintain nutritional value and product quality. In this presentation of the research paper, we will explore the main objective of this experiment is to determine the concentration of vitamin C, or known as ascorbic acid, in a variety of common samples. These include fresh fruit juice, packaged fruit juice, vitamin tablets, and raw fruits and vegetables. To achieve this, a redox titration using iodine solution is performed.
So now, let's move on to the methodology. This is some apparatus and chemicals that needed in this experiment. For apparatus, we need a burette and stand. Then, we need 100 ml or 200 ml of volumetric flask, 20 ml of pipette, 10 ml and 100 ml measuring cylinder, 200 milliliter conical flask, mortar and pestle, and last one is cheesecloth. So for chemical, we need an iodine solution that's 0.005 mole, and last one we need a starch indicator solution for 0.5%. So now I'm going to explain about the procedure. We need to prepare a solution before we do an experiment. So what solution we need in this experiment? The first one is iodine solution, and the second one is starch solution. We go to the iodine solution first. For iodine solution, we need to weigh 2 grams of potassium iodide into a 100 milliliter beaker. Then we need to weigh 1.3 gram of solid iodine and add it into the same beaker. We need to add a few milliliters of distilled water and swirl for a few times until the iodine is fully dissolved. Then, we need to transfer the iodine solution into a 1 liter of volumetric flask, ensuring all traces of the solution are rinsed into the flask using distilled water. Lastly, we need to dilute the solution up to the 1 liter mark with distilled water. And the second one is starch solution. For starch solution, first one, we need to weigh 0.25 gram of soluble starch. Then, we need to add it to the 50 milliliter of near boiling water in a 100 milliliter conical flask. We need to stir until it completely dissolves. Lastly, we need to allow the solution to cool before using it. So now, for sample preparation. First one, we need a vitamin C tablet. For vitamin C tablet, we need to dissolve a single tablet in 200 ml of distilled water. For fresh fruit juice, we need to strain the juice through cheesecloth to remove seeds and pulp, which may block the pipette. Same goes to the packaged fruit juice. So now, for fruit and vegetables. The first one, we need to cut a 100 gram sample into a small pieces and grind it using a mortar and pestle. Then we need to add several 10 ml portions of distilled water while grinding, each time descending the liquid extract into a 100 ml of volumetric flask. Finally, strain the ground pulp through cheesecloth, rinsing it with a few 10 ml portions of a distilled water. Then, we need to collect all the filtrate and washing it in the volumetric flask. We need to make up the extract solution to 100 ml with distilled water. The titration. The first one, we need to pipette a 200 ml a liquid of the sample solution into a 200 ml conical flask and add about 100 ml of distilled water and 1 ml of starch indicator solution. Second one, we need to titrate the sample with 0.005 mole iodine solution. The endpoint of the titration is identified as the first permanent trace of dark blue light color due to the starch iodine complex. So the third one, we need to repeat the titration with further a liquid of sample solution until you obtain concordant results. The titration.
Next, let's look at the example of result. Firstly, for the tablet of vitamin C. Left photo, pre-endpoint, added iodine react with ascorbic acid, giving the reaction solution a clear color. For center photo, throughout the titration endpoint, there was full removal of ascorbic acid. Respondent and the excess iodine combined with the starch indicator to form the color of a pale blue. Lastly, for right photo, when addition of iodine is prolonged, after the endpoint, additional compound of iodine starch is between structured. Then, commercial fruit juice. Left flask. When this flask has not yet reached its endpoint, the solution has the pale yellow color that is characteristic of the fruit juice. Center flask. When titration is complete, all the ascorbic acid is combined with the iodine and any spare iodine react with the starch indicator to produce a dark blue-black complex. Here, the response is dimming of the color of the solution between yellow to the brown gray. Right flask. This represents the consequence of continuing to add only a milliliter of or 2 of iodine solution even after the endpoint has been reached and that additional iodine and starch complex is formed. Next, for freshly squeezed orange juice, left flask, prior to the endpoint, the solution remains in a bright orange color similar to fresh orange juice and its color does not change upon addition of iodine. Center flask, after all the ascorbic acid has been oxidized, then a little excess of iodine added that combined with the starch indicator, turning the solution green in this case. This is where titration stops. Right flask, the solution comprises green color that would darken in case more iodine solution were to be added. Lastly, let's look at the example of result for red capsicum. Left flask, the solution maintained its color before the endpoint. Center flask, when the ascorbic acid is completely oxidized, there is slight excess of added iodine, which lastly form a dark complex with starch indicator to ensure purple color. This is the neutralization point. Right flask, in case additional milliliter or 2 iodine were added to the solution past the endpoint, the solution will assume the deep purple color as indicated in the figure.
We have gone through the volumetric analysis in redox titration, but there are some key applications you might not realize that are happening every day in food industry, which include determining nutrition content, testing for salt and acidity levels because this can help to check acidity and salt content. Same goes to measuring sugar content because it can help to estimate sugar levels in products like juices, soft drinks, and also jams. While for quality control and shelf life, this method helps in monitoring chemical changes during production and storage. For food safety and waste reduction, early detection of unwanted chemical changes helps to prevent unsafe food from reaching the consumers. Lastly, this method can help to ensure the product consistency. Regular checking ingredients during manufacturing can be done using this method. To wrap the topic we have been discussing, redox titration in volumetric analysis is a super useful and reliable method for checking how much vitamin C is in different food products. By understanding how ascorbic acid reacts with iodine, we can accurately figure out the vitamin C contents, which helps to make sure the product meets quality, nutrition and label standards. It is not just easy and affordable, but also really important in food science and manufacturing, especially when it comes to tracking nutrient levels, shelf life, and product quality. Overall, this technique shows how chemistry plays a big role in keeping our food both healthy and trustworthy.